Cool. Welcome back, everybody, to another exciting session of CE 374. Yeah, CE 374U, Urban Stormwater. Welcome back. I've got another exciting lecture for you today. I see that you've all showed back up after the first day. So I see that you are also excited to be here, as I am. A couple quick announcements before I get started. Becky has set her office hours for 2 to 3 Monday and Wednesday. The location is still to be decided, but office hours will be Monday and Wednesday, 2 to 3 p.m. My office hours will be today at 5:30 p.m. So come to see me if you have any questions just about the course in general. Happy to oblige. And homework 1 will be posted tonight. And that will be due approximately 2 weeks from today. Okay, great. Are there any other questions on course logistics before we get started? Yes. It's going to be like the next 3 lectures, and it's going to be a review of open channel flow topics. So for the first 3 lectures, we're going to be primarily reviewing open channel flow concepts, and your homework will be on open channel flow, which you learned a bit of in hydraulics, and we're going to extend that a little bit in this class, okay? Great. Cool. Are there any other questions before I move on? No, nothing? Okay. Great. So, by the way, just bear with me. I'm still getting used to this setup in this room. So it might be a little awkward for the first few lectures, just as I'm getting used to using this tablet in this room. So just bear with me as that happens, okay? Okay, so like I said, for the first 3 or so lectures, we're going to be reviewing open channel flow. Now, this is a topic that I know you covered in CE 356, Elements of Hydraulic Engineering. So before I get started with open channel flow, I want to know just some concepts that you know from CE 356 with regard to open channel flow. What are the names of some concepts or equations that you learned related to open channel flow in your previous coursework? I want your top 10 favorite concepts. Yes. Critical depth. Okay. We will be reviewing that probably next week. Yep.
Super and subcritical flow.
Super and subcritical. Yep. What other concepts or equations do you remember from open channel hydraulics? Yes. Right. So that is what characterizes open channel flow. The pressure is open to the atmosphere. Okay. Are there any other concepts or equations related to open channel flow that you remember? Yes. Energy equation. That's a good one. Yep. Energy equation. Any others you can think of? There we go. Manning's equation. And that is one that we are going to talk about today. Do you remember under what circumstances you can use Manning's equation? It's possible to use Manning's equation under laminar flow, although usually it won't be. It will usually be turbulent, but that's not what characterizes when you can use Manning's equation. Okay, I'll get a few more, and I will reveal the answer later on in today's lecture. But I think I saw your hand.
Is it like a constant error?
That is true. Yep. Are there any other guesses?
The slope.
Yes, the slope of. Yeah, so we'll talk a bit about it. I think I saw 2 more. Any other guesses? Yes. So if Manning's equation applies, you'll be at the normal depth. But there's a condition under which Manning's equation applies, and if that condition is met, it won't be valid. We're going to talk today about when Manning's equation can be applied and what circumstances you can use different open channel flow equations for, because I think really what I want to cover today is how do we model open channel flow, what the different types of open channel flow are. And finally, I want to talk a bit about uniform flow, which is what Manning's equation is used to model. Okay, so for today's lecture, here's what I want to do. We're going to review and classify different types of open channel flow. We're going to talk about the most general case. So we're going to talk about unsteady, spatially varied flow. And we're going to derive the equations that can be used to represent unsteady spatially varied flow, which is the most general type of open channel flow. And finally, we're going to show how we can use some simplifying assumptions to simplify this most general case into the case of uniform flow, which is what you will primarily be using for the purposes of design later in this class. Okay? Great. So let's go ahead and get started. Let's talk about ways that we can classify different types of open channel flow. And there's two basic ways we can classify open channel flow. First, do the depth and velocity vary in time? At any given point in the channel? And second, do the depth and velocity vary in space along the length of the channel? These are kind of the two basic classifications that we're going to use, and it'll determine which equations we can use for design purposes and for analyzing open channel systems. We have to be very careful to use only the types of equations that apply to the problems that we're interested in. So let's review the different cases. First, let's look at the most general case. Okay, so I'm going to talk about unsteady, spatially varied flow. Okay, and I'm going to categorize these into whether they vary in time and whether they vary in space. And I'm also going to, for each of these types of open channel flow, I'm going to give you an example, a real world example of that type of flow. Okay, so unsteady spatially varied flow, this is the most general case. Okay. And it varies both in time and in space. Okay, so this is the most general case. No matter what type of open channel system you're looking at, unsteady spatially varied flow, the equations that we use for this case will always apply. So what's an example of unsteady spatially varied flow that you can think of in an open channel system? Yeah, so basically anything in the real world, because real world systems will generally vary both in space and time. So I'll give kind of just an example here. Let's think of, let's say we have a channel and we have a flood wave propagating through the channel. Okay, so the flood wave will start off at some upstream point up here. And then over time, it will move down the channel and it will vary both in space and in time. Okay, so if you're modeling a flood wave, you need to use the equations corresponding to unsteady spatially varied flow. Okay. Let's look at types of open channel flow that vary in space, but not in time. Okay. So the first kind that you probably looked at in hydraulics is gradually varied flow. So I'll be explicit here. I'll say steady, gradually varied flow. Okay, and as I said, this will vary in space, but not in time. Okay, what's an example of gradually varied flow that you may have encountered in hydraulics? Yes, yes, that's the exact example I was going to give. So often we can just refer to this with kind of the general term backwater effects. Okay, so if you have a profile of the water, maybe you have a dam downstream like this, and the dam is letting out some water, out of the other side. But the dam structure itself will cause the water to kind of flatten out like this. So what we might generally call this is a backwater. So note that this can be, this can be at steady state. It can stay like this and indefinitely, but the flow, the depth and velocity vary over the length of the channel. Okay, so this is gradually varied flow. Another type of flow we might have is steady, rapidly varied flow. Okay, and much like gradually varied flow, this is constant in time, but varies in space. Okay, so can anyone think of an example of rapidly varied flow?
Hydraulic jump.
Right, so that is the canonical example, hydraulic jump. So we have water coming in from downstream at a lower surface elevation. Something happens and it jumps up immediately to a higher elevation. Okay, so here's the water surface. I'll just note that this is a hydraulic jump. Okay. And finally, we have the case where the flow varies neither in time nor in space. Does anyone remember the term, the special term that's used for this type of flow? Uniform flow, exactly right. Okay, so this type of flow only applies when the flow varies neither in time nor in space. So basically the only thing that you can have, here's our channel bottom, is water flowing parallel to the bottom slope. Okay. In a real life example, this might be flow in a aqueduct, conveyance aqueduct. And this would be described normally by Manning's equation. Okay, so it's important to keep these distinctions in mind different equations, different models will only apply to certain types of flow, and it's important to know which type of flow you're dealing with, whether it's possible to simplify to one of these simpler forms like uniform flow, or whether one needs to account for both spatial and temporal variations in the flow. Are there any questions before I move on these types of flow? Right. How many of, is this jogging any memories from 356? Good, good, good. Okay. So what I want to talk about next is this most general case, the case of unsteady, spatially varied flow. And I want to talk about it for a couple reasons. We're going to be looking specifically at the case of unsteady flow. And I want to review this case in particular for a couple reasons. The first reason is that all of the other types of flow that I listed can be derived from this more general type of flow. Okay. All of the other types of open channel flow we've looked at in that previous slide are special cases of this type of flow. The second reason I want to cover this type of open channel flow in particular is because you'll be using a lot of different empirical equations in this class for different types of hydraulic design. Sometimes it's unclear, what assumptions go into them. When that happens, you can always go back to this most general case to think about, what your design needs to be, what the behavior of the system should be. And that's why I want to talk about this most general case of open channel flow. Okay, so let's start with the case of unsteady spatially varied flow. And we're going to derive a set of equations that will essentially always describe the dynamics of flow in an open channel. Okay. The flow of water in an open channel can always be described by the following two equations. Okay. The first is continuity. And the second is momentum. Okay, so no matter what type of system we're looking at, the flow in an open channel has to obey these two equations. Okay, so continuity being a mass balance, and momentum being a force balance. Okay, so this is essentially Newton's second law applied to a body of water. And what we're going to do is we're going to look at how we can derive the most general set of equations that always describe flow in an open channel. And those are called the Saint-Venant equations for unsteady flow. These are the kind of equations that are going to be used in some of the computer models that we look at later in the class. Okay, so first, let's take a look at the continuity equation. And let's see how we can derive a set of equations that always describes the dynamics in an open channel. Okay. So first, let's consider a control volume. We're going to be looking at an element of water in an open channel. So I'll draw the bottom. This is the bottom of the channel here. Okay, we have some water surface up here. And let's define a control volume inside of this channel. I'm going to define it with this little green boundary here. So we're just looking at the mass balance within this control volume here. So within an open channel, we have flow coming into this control volume. I'll call this Q in. And we have flow coming out of this control volume. I'll call it Q out. Okay, and at the top of the channel, pouring over the side, let's say we might have some lateral overflow into the channel coming into the top. So this might be rainfall, it might be runoff from the side. And and we will denote this by undercase QL. So this is the lateral overflow per unit length of the channel. And finally, let's just define the dimensions of the control volume. Let's say the length of the control volume in the longitudinal direction is delta X, okay? And I'm going to go ahead and draw a cross-sectional view of this control volume as well. So this is looking straight on into the channel. Okay, we have that the height, the depth of the water, let's call it H. And let's say that the wetted perimeter, so that is the perimeter that water is in contact with, we'll call that P, capital P. Okay, and let's say that the total area, the cross-sectional area of the water, let's call it A. Okay, so this is our control volume. Continuity essentially states that for any physical fluid system, the change in the mass within that control volume has to equal the mass in minus the mass out, okay? So for continuity, all we're saying is that the rate of change of mass within the control volume is equal to mass flow rate in minus mass flow rate out. Okay, so we can express that mathematically. I'll just give you a second to write that down. Okay, so we have that the rate of change of mass within the control volume has to equal the mass flow rate in minus the mass flow rate out. The rate of change of mass within the system we can describe as the density rho. Let's just look at this over a discrete time interval. Okay, so we're going to look at this over a discrete time step delta t, and we're going to look at it over a discrete spatial interval delta x. Okay, so the rate of change of mass within the control volume is equal to the density times the volume at time step t plus delta t minus the volume at time step t divided by our time step delta t. Okay, so note that this is the rate of change of the mass within our control volume. Okay, and we know that this has to equal the mass flow rate in minus the mass flow rate out. Okay, so that will be equal to our density rho times quantity Q in, our flow into the control volume, minus Q out. And is there anything else I'm missing here? The lateral, right? Plus our lateral discharge in times the length over which the lateral overflow is being applied, which is delta x. Okay, so this is the mass in minus mass out. Okay, and we can simplify this a bit. So what's another way that we could express the volume in terms of the variables that we know? Oh, sorry? Right, so this top term here is delta V. We can re-express this in terms of two other variables that we have defined here. Yeah, so it's the area times delta x. The volume in our control volume is equal to the cross-sectional area times our length, delta x. Okay, so let's go ahead and re-express that. We have that the rate of change of mass, we can write in as rho times, actually delta x is a constant, so I'll just bring it outside. Rho delta x times the cross-sectional area times t plus delta t minus the cross-sectional area times t all over delta t is equal to, and here we just have the same expression over again, rho times flow rate in minus flow rate out plus the lateral overflow into the channel. Okay, so we can simplify this a bit more. Note that we can divide by the density on both sides. It doesn't really matter here. So let's go ahead and cross that out. And we can also divide by this delta x here. And what we get is the following expression: area, cross-sectional area at time t plus delta t minus cross-sectional area at time t all over delta t is equal to q in minus q out over delta x plus the lateral overflow. Okay, so I've just divided by delta x on both sides. I've divided by the density on both sides. Okay, and actually, I'm going to rearrange this here. I'm going to do it in place to save some space. I'm going to say, I'm going to rearrange it so that we have q out here, q in here. And then I'm going to set this equal to the lateral overflow. So all I did was I moved this term over to the left-hand side. And now what I want to do now is think about what happens to this when we make delta x and delta t very small. Okay, so as we take the limit of this equation, as the time step becomes very small and as the spatial step becomes very small, what we end up with is the following partial differential equation. Okay, what we end up with is the continuity equation. This is how you'll see it expressed. If you're looking at how it's expressed in a computer solver, it'll be expressed in the following form: the partial derivative of the area with respect to time plus the partial derivative of the discharge with respect to our spatial coordinate is equal to the lateral overflow into the channel. Okay, so this is the continuity equation. Basically, what this is stating is that the change in mass within the control volume is equal to the flow in minus the flow out. Okay, so this is how it's expressed in differential form. Okay. Are there any questions with how I derived this equation here? So note, this is taking the limit as delta t goes to 0 and as delta x goes to 0. Right. Are there any questions on how I derived this equation here? No? Okay, well, let's keep going. The second component of the full equations for unsteady spatially varied flow is the momentum equation. So let's take a look at the momentum equation. This one is the trickier of the two to derive. But once you'll see it, you'll understand that it's not as mysterious as it looks at first. What we're going to do is we're going to apply a force balance to our fluid control volume. And from that, we will know exactly what the dynamics inside of that control volume are at all times, okay? So let's look at our control volume again. Okay, so this is our portion of open channel again. We have our same control volume as before. But in this case, instead of applying a mass balance, we're going to apply a force balance to this control volume. Okay. So let's just brainstorm here. Actually, first, okay. So the momentum equation is essentially Newton's second law applied to a fluid volume. Okay. Does anyone remember what Newton's second law looks like? Sorry? So close. Newton's second law, you may, going back to physics for 101, you may have seen it in the following form, that the sum of forces on an object is equal to mass times the acceleration. Okay. So the same equation that you apply to point masses also has to apply to a fluid volume as well. Okay. Except in this case, we're not looking at the acceleration. Note that this equation here isn't how Newton's second law was formulated originally. Does anyone know how Newton originally stated it in his original article? Right. So the way that the Newton's second law was originally formulated is that it stated that the sum of forces acting on an object is equal to the time rate of change of the momentum. Okay. So note, this is Newton's second law. This has to apply to any physical system, meaning it has to apply to our open channel system as well. Okay, so we're going to go and we're going to apply Newton's second law to our open channel system and see what equation we get from that. Okay, that's what we're going to do in this next section. And we know that it has to apply because any physical system, Newton's second law has to apply. Okay, so taking a look at our control volume, let's just brainstorm here. What forces are acting on this fluid control volume here? Gravity, great. Let me write these down. Okay, so the forces we have the gravitational force. Okay. What other forces do we have acting on this control volume? Sorry? Atmospheric pressure, that's true. So I can just draw that. Atmospheric pressure will be acting normal to the surface. And so what we're primarily interested in is the force balance in the longitudinal direction throughout the channel. Friction, that's another one. So friction will be acting this way. Okay. Are there any other forces we can think of? And there's, oh, yes? Shear. So that would be related to friction. Mm-hmm. Yes? Right. And what's the name for the weight of the water in terms of the force? There's a special name for it. Hydrostatic force. Okay, so let's draw that out here. Great. So it's similar to what you mentioned with the atmospheric pressure. Here, the primary pressure force we're interested in is the pressure force of the water itself. Okay, so that's going to be acting on both sides here, both sides of our control volume. Let me write that down. Actually, I'll write it down over here. Okay. So for completeness here, let me draw a cross section. Okay. Again, we have the depth of the water in the channel, which I'll call H. We have the wetted perimeter, which we're going to need, which I will call P, capital P. And we also need the depth of the centroid of this area for a reason you'll see soon. So actually, we're also going to need the depth of the centroid of this cross section. Okay, so let's go ahead and write down the expressions for each of these forces. Okay, the easiest one is the gravitational force. So we know that the gravitational force, the weight is equal to mg, right? Where g is the acceleration due to gravity. The mass of our control volume, we derived this before. It's just the density times the cross-sectional area times delta x, all times g, okay? So that is the gravitational force in the downward direction. We're interested in the component of the gravitational force in the longitudinal direction, right? So this is going back to physics 101. Let's say that the channel bottom slope has an angle of, let's call this angle theta. Okay, so our gravitational force, I'll call it Fg. This is going to just be equal to this expression here times sine theta. Okay, so this is kind of just going back to your old physics class. The gravitational force in the longitudinal direction is equal to the density times the cross-sectional area times delta x times g times sine of theta, where theta is the slope of the channel bottom. Okay, sorry, not the slope, the angle, the channel bottom. Okay, so the frictional force we can describe as being equal to essentially the area that's in contact with the water times the mean shear stress. Okay, so the shear stress we're going to call tau naught. And the area that's in contact with the water, what is that? Perimeter times, perimeter times delta x, okay? So this is the area in contact with the bed. And this here is the shear stress. Okay, and the hydrostatic force is equal to the pressure times the area, right? Specifically the pressure at the centroid of the fluid times the area of the cross section. Okay, so we can express that as our hydrostatic force FH is equal to, we're interested in, the pressure applied at this upstream face minus the pressure applied at this downstream face here. Okay, so the pressure applied at the upstream face, the total force is going to be rho g times the height of the centroid at the upstream. So I'll say HCN times the area at the upstream end, AN. Okay, so this is the hydrostatic force at the upstream end. The hydrostatic force at the downstream end is going to be equal to the density times the pressure. Sorry, this whole component here is the pressure at the downstream face times the area at the downstream face. Okay, so that means that the hydrostatic force is this expression minus this expression. Okay, so it's going to be rho g times HC in, that's the height of the centroid at the upstream end, times the cross-sectional area at the upstream end, minus the height of the centroid at the at the downstream end, times the cross-sectional area at the downstream end. Okay, now let me just pause for a second. I know this might seem rather complicated. We're getting pretty advanced right now. I just wanted to let you know. So we're looking at the most general case. So it is going to be a bit complicated. We're going to simplify this as we move on. Okay, but I think it's important to understand where these equations ultimately come from. Okay. Okay. Are there any questions on this force balance before we move on? Okay, you're doing a great job so far. I just wanted to reinforce that this is supposed to be a bit complicated and difficult. Okay. Okay, great. So we have all of our forces. Okay. Now what we need to do is we need to show that the sum of the forces acting on our fluid volume is equal to the rate of change of the momentum. Okay. So let's look at the rate of change of the momentum. We know that the net rate of change of the momentum of our fluid body is equal to the rate of change of momentum inside the control volume plus the momentum flux through the control volume. So the momentum flux out of the control volume minus the momentum flux into the control volume. Okay. Okay, so expressed mathematically, we can write this as follows. We have that the rate of change of momentum in the control volume. Let's discretize it again. Let's just look at our control volume with length delta x at a time step delta t. Okay, so this is going to be approximately equal to the mass in the control volume at time step t plus delta t times the velocity of flow at time step t plus delta t minus the mass at time t times the velocity at time t divided by our time step delta t. Okay, so that this portion is the rate of change of mass, rate of change of momentum within this control volume. Okay. Plus our momentum flux through the control volume. So this is the component of the momentum, the net flux of momentum through the control volume, okay? So this will be equal to the mass flow rate out times the velocity out minus the mass flow rate in times the velocity in. Okay, so this is the momentum flux through our control volume. Okay, so let's simplify this a little bit. From before, we know that the mass of the water in the control volume is equal to the cross-sectional area times delta x, right? So let's write that out again. We have that the mass is equal to the density of the fluid times delta x times the area, cross-sectional area at time t plus delta t, times the velocity at time t plus delta t, minus the area at time t times the velocity at time t, Okay. All over delta T. And then we can factor out the density here as well. So this will be rho or density times. What happens if we factor out the density from this term here, from this mass flow rate term? What does it become? Sorry? Right? Yep. And another name for that would be the flow rate, right? Exactly. So this will be Q out times the velocity out minus the flow in times the velocity in. All right. And what is this term here equivalent to? What is the area times the velocity? What is the area of flow times the velocity of flow? The flow rate, right, exactly. So we can simplify this. This becomes the density times the spatial increment delta x. And this term in here just becomes the flow rate at time t plus delta t minus the flow rate at time t all over delta t. Okay, and over here we have rho times the discharge out times the velocity out minus the discharge in times the velocity in. Okay, I know this is complex, so thank you for sticking with me. You're getting super advanced for getting this far. So was there a question?
To clarify, like, for example, that's not to the this.
Yeah,
When I look at it's descriptive, I look at exponents.
right. Right. So it's not an exponent in this case. It's just a superscript stating the flow at time step t plus delta t. Okay. Thank you. Yeah. Okay, so we're almost there. Okay, so here we have our expression for the rate of change of momentum. All we have to do now is we have to say that the rate of change of momentum is equal to the sum of forces. Okay, so we're going to take our expression for the rate of change of momentum. That's what we have right here. And we're going to equate it to our sum of forces that we wrote down here. Okay, and let's see what pops out when we do that. Okay, so let's write the expression for our rate of change of momentum. Okay, we have Q, actually, right? So we have the density times delta x times quantity flow at time t plus delta t minus flow at times t divided by delta t. Okay, so that's the rate of change of momentum within the control volume plus the density times Q coming out of the control volume times the velocity coming out of the control volume minus Q coming into the control volume times U coming into the control volume. Okay, and we're going to set this equal to our forces from earlier. So we have our hydrostatic force. That's going to be G times our density times H, our centroidal height at the upstream face, times the area at the upstream face, minus the centroidal height at the downstream face, times the area at the downstream face, plus our gravitational force. So that's going to be G times the density times the area, cross-sectional area times delta x times sine of theta. Okay, plus our frictional force. And that is written as negative tau times the wetted perimeter divided by the density. Okay, we're almost there. What I'm going to do is I'm going to divide by the density, and I'm going to divide by delta x, and I'm going to see what comes out, okay? So if I divide by the density and delta x, let me just do this, let me do this in place. So I don't have to write this out all over again.
Sorry, the
Mhm.
original force actually divided by density delta x.
Oh, sorry, you're right, you're right. You're right. Wow. You're sharp out there, thank you. All right, so yeah, it should be negative tau, or shear stress times the wetted perimeter times delta x. Okay, so I'm going to divide by the density and delta x. And what we get if we do that, I'm just going to do it in place here to save some space. This goes away. This density here goes away. We have a delta x in the denominator. And this becomes g. And we get a delta x in the denominator as well. Here we remove the rho term, the density term, and we divide by, sorry, the delta x comes out of here. So we just have a. And here the delta x comes out, and we get our density in the denominator now. Okay, and there's a couple more simplifications I'm going to apply before we write out our final form for the momentum equation. I'm going to use the small angle approximation. Okay. And I'm going to say that sine theta is approximately equal to the channel bottom slope. Okay, so this is the small angle approximation. We can say that this sine theta here, it's approximately equal to the channel bottom slope, so S naught. Okay, and the other simplification I'm going to apply is I'm going to define a term called the friction slope. To simplify this term here, okay, the friction slope will be equal to our shear stress times the wetted perimeter over the acceleration due to gravity times the cross-sectional area times the density. Okay. And so this term here, we can rewrite as GA times the friction slope. Okay. And what happens when we apply these approximations and we do the same trick as before, we take the limit as delta t and delta x go to 0, we get the final form for the momentum equation. Okay. And what you will get is the following. dq by dt plus dqu by dx plus g times the cross-sectional area times dh dx minus the bottom slope plus the friction slope is equal to 0. And with that, we have done it. So all we have to do now is go back and add our continuity equation from before. Okay. We add our continuity equation. We get dA by dt plus dq by dx is equal to the lateral overflow into the channel. Okay, so let's take a pause there for a second. I know that was probably a lot. But what we have here is a set of equations that describe open channel flow for essentially any case you can think of, okay? So no matter whether it's varying in space, varying in time, no matter whether you're looking at gradually varied flow, rapidly varied flow, these set of equations will always apply. And does anyone remember what these two equations are called when they're paired together? Has anyone seen these before? Any idea? So these are called the Saint-Venant equations. Okay, so this is the most general form of the equations describing open channel flow. Okay. These will always apply no matter what situation you're looking at. Another name for these that's sometimes used is the dynamic wave equations. Okay. And let me go back and kind of describe what each of these components is, okay? So this describes, let's look at the continuity equation first. Okay, this describes I'll write it in green. So the continuity equation is essentially a mass balance. It's stating that the change in volume, or I'll say the change in mass with time in our control volume essentially has to equal the flow rate in minus the flow rate out along with any added overflow into the channel. Okay, so this is flow into channel from outside. The momentum equation, as I described it before, is essentially stating that the change in momentum within a control volume has to equal the sum of the forces acting on that control volume. Okay, so our forces are the hydrostatic, the gravitational, this is the core part corresponding to the gravitational, the frictional, okay. This here is the change in momentum within the control volume. And this is the flux of momentum through the control volume. So these equations essentially describe the dynamics of the water and how it will move in any case you can think of. Yes. That's a good question. Yes, actually, if you can look up and find the reason why, you can express it in this form, you can get an extra credit point. That's a good question. And it's not an easy one to find. So yes, if you can find an answer to that, let me know, and I will give you an extra credit point. Okay. Great. So, how do we solve these equations? Does anyone know how we solve equations like this? Remember the technique we use to solve equations that look like this? Does anyone remember? I'm messing with you. You can't solve equations like this. This is a coupled nonlinear partial differential equation. There is no closed form solution to a system like this? The answer is you have to simulate it, basically. Okay, to solve an equation like this, you take your open channel, you divide it into small segments, you define the height, the depth of the flow, the discharge within each of these little chunks, and you simulate it using a large system of equations, okay? So to solve, you have to do it numerically. Okay, so in general, the Saint-Venant equations are not easy to work with. There's generally no closed form solutions to them. You have to simulate them. And even if you do, it's not easy. Okay, so these are coupled nonlinear partial differential equations. They often have issues with numerical stability. They'll blow up. They often break down when you get rapidly varied flow. They break down when the depth of water approaches zero. So in general, they're not easy to work with. So as engineers, often what we do is we develop simplifications to these to allow us to do design more easily, okay? So let me go through various simplifications we can apply to these equations to make them easier to work with. And these simplifications will be what you will work with in the software models later on in this course, okay? So note, there are models that solve these equations. EPA SWIM solves these equations. If you run the Unsteady flow solver in HEC-RAS, it can solve these equations. But many times you don't need to solve the full Saint-Venant equations, and various simplifications will do. So today I'm going to talk about a couple of those simplifications. And then in the next lecture, we're going to talk about when you can use those simplifications and when you can't. Okay, are there any questions before I move on? Great. Okay, so let's talk about a couple of simplifications we can make to this equation. And let's see, is it possible to copy this slide? I don't think I know how to do it. So I will just go ahead and write it down over again. So let's look at simplifications to the Saint-Venant equations. Okay, and first we're going to look at simplifications that still incorporate the time varying dynamics, but do so in a more simplified and easy to compute way. Okay, so these are dynamic simplifications. These are used by a lot of the solvers that we're going to be looking at in class, okay? So let's take our equations from before. The first simplification we're interested in is called the diffusive wave. Okay, so remember our Saint-Venant equations, they're sometimes called dynamic wave. That's what they'll be called in SWIM, for instance. But the first simplification we can apply is the so-called diffusive wave. Okay, so what we have here is the continuity equation will stay the same. So we have dA over dt plus dq over dx is equal to the lateral overflow. And then we have our momentum equation, but we're going to simplify sorry, this is dq by dt. We're going to simplify the momentum equation to make it a little bit easier to work with, okay? So our original momentum equation was dq by dt plus dqu by dx plus g times the cross-sectional area times quantity dh by dx minus the bottom slope plus the friction slope is equal to 0. For the diffusive wave, we're going to keep the continuity equation exactly the same, but we're going to remove the momentum, the change in momentum terms from the momentum equation. So this will go to 0, and this will go to 0. Okay. So essentially, we're removing the change in momentum from the momentum equation. We're assuming that the system is at static equilibrium, right? So in this case, the sum of forces is equal to 0. And next time we'll talk about what that does in terms of what we can represent. In particular, we've removed the ability to model very fast moving flows where the inertia matters a lot, okay? The next simplification we can apply is called the kinematic wave. Who's heard of this term before? Who's heard the term kinematic wave, right? What context have you seen that term in before? Do you remember? You don't remember? Cool. Has anyone seen the term kinematic wave before? Do you maybe, right. Yeah, so SWIM solves this. So does HEC-HMS. There's another context in which you might have seen kinematic wave before that has nothing to do with water. Does anyone know what it is? Does anyone remember transportation? So the flow of cars within a roadway can often be modeled using the kinematic wave equation. Okay, that's another context in which the kinematic wave equation is used. Okay, so with kinematic wave, continuity stays the same. Okay, I'm going to write out the full momentum equation again. Okay, with our sum of forces. And for kinematic wave, we're going to simplify it even further. So first, the system's going to be at static equilibrium. The sum of forces is going to be equal to 0. And we're also going to remove this hydrostatic term. So under the kinematic wave formulation, the gravitational force is going to be equal to the friction force. So friction and gravity will balance each other exactly. Can anyone think of what that's going to take away when we go to model our open channel system? What can't we represent anymore? Sorry? Sorry? Deep channels? Kind of. So what type of flow can't we represent anymore if we don't have hydrostatic? If the hydrostatic force is assumed to be equal on both sides, yes? It can still represent laminar. So we're removing we're essentially saying that the difference in pressure on the different sides of the control volume is equal. Yeah, so essentially what we won't be able to represent is backwater. We won't be able to represent backwater anymore. So if you have a system in which you have impoundments, any kind of control structures, kinematic wave will not be able to represent the backwater effects imposed by those structures or any other kind of changes in the slope of the water surface. So that's an important thing to understand and appreciate when you are modeling these systems, okay? Okay, so I've got a couple more simplifications to show you. I think we leave at 4:45, right? Okay, yes. So the diffusive wave, we're essentially assuming that the system is at static equilibrium. Okay, so I'll actually draw out what this simplification can't represent. Let's say you have, actually, I'll do it over here, okay. Let's say we have a kind of like this little, maybe parabolic channel shape here. And let's say we have a hose or something. Say we have a hose. And we're shooting water down here. We're letting the water kind of just shoot down out of the hose. In the full Saint-Venant equations, this water will what'll happen with this water in the actual real world system, if you're shooting water very quickly from a hose into a parabolic kind of channel shape, what'll happen with the water as it comes to this end? Yeah, it'll fly out because the water has momentum or inertia, right? If we remove these terms, we won't be able to represent very fast moving flows of this type where the inertial component matters a lot, okay? So for real world open channel systems where you're looking at floods, inertia very rarely actually matters. The momentum of the flow itself very rarely matters, which is why often diffusive wave or kinematic wave are used in that context. So I'll just finish my thought here. Cannot represent this. High momentum flows. Okay, and also, let me just finish this thought here. Kinematic wave cannot represent backwaters. So keep those in mind when you go to model these systems later in class. If you have a system where backwater effects are important, you're going to have to use either diffusive wave or the full dynamic wave equations as provided in these solvers. Okay, you got 3 minutes. I'm gonna try to finish out. So we looked at simplifications of the Saint-Venant equations that are dynamic, that have some time varying dynamics. Let's look at simplifications to the SVE, the Saint-Venant equations that are static. What do I mean by static? I mean that the dynamics don't vary with time. They stay the same in time. Okay, so the first one that we're interested in is our example from before, gradually varied flow. So let's write out our equations from before. We have dA by dt. This is continuity equation. dA by dt plus dq by dx is equal to the lateral overflow. And in the momentum equation, we have dq by dt plus dqu dx plus ga. I think my mic just fell off. I'll just talk really loud. Ga times dh dx minus the bottom slope plus the friction slope is equal to 0. Okay, so for the static case, all our time derivatives go to 0. Okay, so this goes to 0, this goes to 0. And we're also going to assume that there's no lateral overflow. So this goes to 0, which means that this term here also has to go to 0. And what you end up with is just this part of the momentum equation. If you rearrange this, you get the same gradually varied flow equation that you got in hydraulics, okay? The final form that we're interested in is uniform flow. And that's basically the most simplified we can get. Okay, this is what we're going to be primarily working with in this class, but it's important to remember that this is a simplification of a simplification of the real world dynamics that we're interested in. So let's start with continuity. I promise this will be the last equation I write today. And we have momentum. dqu dx plus ga dh by dx minus S naught plus friction slope is equal to 0. So just like before, all our time derivatives go to 0. This is the system that is static in time. Our lateral overflow is 0, which means that the mass flux through the control volume, it's equal. We'll also assume that this term here is equal to 0. And we'll assume that the hydrostatic pressure difference is also equal to 0. So in summary, for uniform flow, we have that the bottom slope is equal to the friction slope, or in other words, the gravitational force matches the frictional force exactly and is constant in time. Okay, so that's when you can apply Manning's equation. That's my conclusion for today. Thank you.
The centroid is not the centroid in the Saint-Venant. That's because we are assuming that the area of is uniform across the beach. So, because of that,
Cool. Let me just stop the recording real quick.
yeah. So you guys have